This lecture is entitled The Origin and Evolution of the Universe and corresponds to the third subsection of section 1.1. In 2003, astronomers used Hubble Space Telescope to look back in time to within 1 billion years of the Big Bang. Each spot is a galaxy consisting of billions of stars. The light from the smallest, most redshifted galaxies originated nearly 14 billion years ago. In 2009, the shuttle serviced Hubble, enabling the creation of the extreme deep field invisible and infrared light, attempting to look at the very first galaxies in the universe. The early universe was mostly hydrogen, with some helium and lithium. These light materials collapsed to form stars. Stars generated energy by nuclear fusion, creating heavier elements, as heavy as iron in the process. Dying stars eject those elements into space. Massive stars die with a supernova, which fuses elements heavier than iron. From the debris clouds, new stars and planets and humans form.
We understand that during the day, light from the sun scatters through the atmosphere, making it bright. But if the universe were infinite in size and eternally static, always unchanging, then wouldn't the billions of galaxies filled with billions of stars also make the night sky bright? It would always have time to reach us if it was infinitely long. This was Olber's paradox, and I hope you watch the video explaining how this night sky conflicts with the assumption of an infinite and eternal static universe. Stars generate energy by nuclear fusion, creating heavier elements in the process. So the early universe, right after the Big Bang, only had hydrogen and helium and a few of the lighter elements, very, very few. Stars use nuclear fusion to create the heavier elements. Dying stars eject those elements into space, and then new stars and planets and humans form from those. We are star stuff. There was a star here before our sun that had a supernova event to create the heaviest elements in our Earth, and we are a second-generation solar system.
Here is a periodic table of the elements showing the process that created them. The Big Bang event produced the hydrogen and helium of the universe. In physical cosmology, Big Bang nucleosynthesis, also known as the primordial nucleosynthesis, produced lithium and beryllium in the early universe. The first publication that outlined the theory of light element production in the early universe was one written by Ralph Alpher in the 1940s with his advisor George Gamow. Formerly titled The Origin of Chemical Elements, it was published in April 1948, and Gamow, as a joke, Alpher made the author list Alpher Beta Gamow, including his friend Hans Bethe in absentia to make a play on the Greek letters alpha, beta, gamma. Bethe, who was a peer reviewer of the paper, removed the in absentia designation and made himself a full author, undoubtedly with some profound contributions. The Alpha Beta Gamow paper is a famous paper for that clever pun and is often referred to as the alphabetical article. More importantly, what the paper discusses is that all the elements that are heavier than lithium were created by later in stellar nucleosynthesis in evolving and exploding stars. Processes involving fusion of elements lighter than iron are possible in evolving stars, but processes involving fusion of iron and heavier elements, because they require input energy, are only possible in exploding stars, in supernova. The very heaviest elements are man-made in atom smashers. In summary, the universe began 13.8 billion years ago in an event known as the Big Bang. The only chemical elements in the early universe were hydrogen and helium. Fusion processes in the cores of stars produce heavier elements up to iron. Supernova events produce elements heavier than iron. Hydrogen is the most abundant element in the universe.